All right, let's talk about matrix inverses. How to take a matrix and define something called like the opposite of it in a sense, so that we can do something sort of like matrix division. So for example, with numbers, if you take something like the number 2, you can multiply it by its inverse, which you write as 2 inverse, and you get the number 1, right? And then number 1 has special properties. So, like, for example, if you do 1 times anything, or anything times 1, it's the same thing with numbers, it doesn't change it. And with numbers, it's not too bad. The multiplicative inverse of 2 is really just the fraction 1/2 or 0.5. With matrices, it's a little bit more complicated, but what we're trying to do is still the same idea. We're trying to take this matrix A and get a multiplicative inverse so that when you do A inverse multiplied by A, using whatever definition of matrix multiplication you want to use, then you get the identity matrix. Which, remember, the identity matrix functions kind of like the number 1. You can multiply I by any vector and it won't change it. You could actually multiply I by any matrix and it won't change it. Remember, just as a quick review, it's usually going to be something like 1, 0 with some number of zeros, and then with ones all along that main diagonal, however far it goes, with everything else being 0. And the other thing that has to be true is you also need to get this by doing this matrix multiplication in the opposite way. And instead of doing A inverse times A, you need to be able to do A times A inverse and get the same thing. And it's not actually obvious that these two things always work out the same way. Like if it's possible to do A inverse times A and get I, it's a little bit tricky to show that the other way also works. But it turns out if one of these ways works, the other one does as well. Okay, so that's what it means to be a matrix inverse. Let's do a quick example of one. Let's say A is the matrix 2, -3, 5, -7. Let's check that A inverse, which I'll just give it to you this time. We're just going to check that it works. So we just want to make sure that this is actually A inverse and that A is invertible. So to do that, let's do A times A inverse, but I'll think of it this way. Remember, one of the most important definitions of a matrix times another matrix is we get this new bigger matrix, or maybe it's not bigger, maybe it's smaller sometimes, depending on the sizes, but we get this new matrix where each of the columns of it are the result of doing A times the respective column of B. So that linear combination of the columns of A using the entries from that first column of B as weights, etc. We're going to do the same idea here. So to get this first column, it's going to be A, the 2, -3, 5, -7, multiplied by this column here, and then 2, -3, 5, -7, multiplied by the -5, 2 column. And so again, we're using A times this column here, and then A times this column here. So then let's actually work this out. We're going to do -7 times this one is going to look like just skipped writing some of that out to make it a little faster. And then if we actually want to do this linear combination now, we're going to get negative 7 times 2 is 14 plus 3 times 5 in that first column is going to be a 1, and then positive 21 minus 21 in the second one right there. And so here we're going to get negative 10 plus 10 in that first row, and then 15 minus 14 is 1 there. So doing this A times the first column of A inverse gives you that 1, 0, and doing A times the second one here gives you that 0, 1. So you can kind of see that another way of seeing this is that the columns of A inverse are the solutions of this vector equation, like AX equals E1 and AX equals E2, is kind of a nice way to think about how this works. So I'm actually just checking it with A times A inverse. You could also check A inverse times A if you want. Now let's look at this next example here, where A is has columns 4, 7, and negative 8, 14. And the first thing you might notice about that is that the second column is negative 2 times the first column. And it turns out that when you have a situation like that, where you have linearly dependent columns, it's going to turn out that that means the matrix does not have an inverse. And I kind of want to show why that works here. So let's think about solutions of the homogeneous equation. Well, of course, x is always, x equals 0 is always a trivial solution. You could always do 0 times one column plus 0 times the other one and get the 0 vector, and that's fine. But we can get a non-trivial solution here because we can get, let's see, if we do whatever we have here, we're going to do that times the first column. In our second entry, we're going to do times the second one, and we want to get 0 as a result. So let's see, if I do 2 times 4, 7, that will give you 8, positive 14, and then you can just do 1 times the second one. We'll cancel that out. So just 2, 1 should work. So in other words, let's just write out that this A times 2, 1 gives you 0, 0. So A times 2, 1 is 0, 0. So if you multiply that by any matrix B, that as long as it's defined, let's say any square matrix B. So I'll do B times this on the left, and also B times this on the left. And thinking of B times A times 2, 1, usually the parentheses would be here following the order of operations strictly, but you know it's okay to move it around. That's associative that way. So you can write this as B times A times 2, 1. Like so. And then let's think about what any 2 by 2 matrix times 0, 0 is. Well, 0 times that first column plus 0 times the second column is always going to give you a result of 0 still. So if this, if you multiply A by any matrix, then it turns out that that times 2, 1 is still going to give you 0. So that means B times A cannot be the identity matrix, no matter what. Because if it was the identity matrix, then the identity matrix times anything, including 2, 1, would just leave it unchanged. and not give you 0 as a result. So the fact that you have these linearly dependent columns means there's some way to get 0. That's always going to mean that there's no way to multiply that matrix by any matrix on the left, at least, and get the identity matrix, which means it's not invertible. So B cannot be equal to A inverse here. Something else I want to notice here is that if you're familiar with the determinant of a 2x2 matrix from Calculus 3 maybe, you'll notice that if you do the determinant of this, 4 times negative 14 minus 7 times negative 8, you will get negative 56 plus 56. So by the way, the determinant of a 2x2 matrix is the result of doing the first diagonal, the main diagonal, those two numbers multiplied by each other, and then subtract the result of doing the other two diagonal numbers multiplied by each other. And you get 0 here. In general, this is always going to be 0 when your matrix is not invertible. And we're going to sort of explain why that is in a little bit. Okay, let's look at a kind of more systematic approach to finding the inverse of a matrix. If you're just given the inverse, what you're trying to find is a 2x2 matrix. Let's give the entries of it some names. Maybe let's call it W, X, Y, and Z. We're trying to find those 4 numbers so that when we do A times A inverse, what we get is the identity matrix. In the columns of the identity matrix are, of course, E1, also known as like the I unit vector, and E2, also known as the J unit vector. So that's the goal. But what I want to do is think about the result of this product as being where one column, the first column here, is going to be the result of doing A times WX. So that's going to look like 1, 2, 3, 7 times that WX. And the result of doing this should be the first column of the identity matrix, 1, 0. So we should be able to get that W times, or sorry, that A times that WX vector to become 1, 0. And likewise, we should be able to do the, A times the YZ vector to get 0, 1. And this is, again, just the one of the definitions of matrix by matrix multiplication. And so we can think of this as trying to find this W, X, Y, and Z vectors here. It's basically the same thing as trying to find solutions to these 2 vector equations at the same time. One, that this 1, 2, 3, 7 times WX equals 1, 0, and also we simultaneously want to find out what makes 1, 2, 3, 7 times YZ be equal to 0, 1. Now, in order to do that, we'd normally be row reducing 2 augmented matrices. Like so. There'd be this one would be finding the WX that gets you 1, 0, and then row reducing this one would be finding the YZ that gets you 0, 1. So instead of thinking of row reducing those 2, whoops, I got this off the edge of where you can see. Instead of row reducing those 2 separately, you can maybe see that whatever operations you're going to be doing to row reduce one of them are the same operations you'd be doing to row reduce the other one. For example, you're going to want to make the 1 here a pivot position and probably do negative 2 times row 1 plus row 2 to get a new row 2. You'd be doing the same thing here with this 1 and this 2 in the second one. So instead of doing it separately, why not just like make an extra augmented matrix where we just have one 0 column and then also a second 0 1 column. So we get this extra augmented matrix here, and we can just row reduce each of them at the same time. So I'm going to do a regular -2 times row 1 plus row 2 to get the new row 2. That's going to be a 0 here. -2 times 3 plus 7 is 1. And then -2 times 1 plus 0 is going to be -2. And -2 times 0 plus 1 is still 1. And do one more operation here to get it. So we need to clear this 3 away to get it into row reduced echelon form. So we're going to do -3 times the first row plus, sorry, -3 times the second row plus the first row to make a new second row to clear away that -3. So I'm going to actually leave the second row alone. Whoops. And so it's going to be -3 times -2 is 7. Wait, what? I'm sorry. -3 times -2 is 6. Right, and that plus 1 is 7. That's what I was thinking. And this is just going to be -3. So now this extra large augmented matrix is in reduced echelon form. We can write this as equations again. The first column here, 7, -2. Remember, we're thinking that was where we started with the 1, 0 here, and that corresponds to the equation that has w and x in it. So I'm going to write that as 1 times w plus 0x equals 7, and 0w plus 1x equals -2, which of course means w equals 7 and x equals -2. And you can do the same thing with the second column here. The system of equations that we were thinking of when we were row reducing this was originally a times yz equals 0, 1. So that means it's equivalent to saying 1y plus 0z equals 0, equals -3, and 0y plus 1z equals 1. So in other words, y equals -3 and z equals 1. So this is really telling you the second column of what the inverse should be. We've actually pretty much finished the problem here and gotten a inverse. It's just going to be 7, -2, -3, 1. Now this process for finding a inverse actually works in general. You can row reduce this augmented matrix that you make by putting A on the left and the identity matrix on the right, and row reducing it will be turning it into these row echelon form systems, one for each one of these columns, that will tell you what the inverse should be. So that's my explanation for why this fact works. A square matrix A is invertible if and only if its row equivalent to I. I'm not exactly proving that part of it, but the example kind of illustrates why that fact is true, I think. And if it's row equivalent to I, then you can make this big augmented matrix and row reduce the A to row echelon form, which should look like I, if it is actually invertible. And in doing so, the I part is going to turn into a inverse. So let's apply that logic to finding the inverse of a 2 by 2 matrix in general. Maybe there's a nice formula you can use so you don't have to row reduce stuff all the time. So here's the matrix we want to reduce. I think a reasonable first step is to try to cancel out the C here by doing a row replacement operation. But before that, maybe I want to multiply both sides by, the second row by A, just to do a scaling operation to make it work out. So if this is A times C in this position, then you'll be able to do negative C times A, and then add that to this new second row to clear it out. So that will give you A times C and A times D here, A times 0 and A times 1. And leaving the A and the B and the 1, 0 alone. So then I'm going to do a row replacement operation, doing negative C times this first row and adding that to the second row to get a 0 there. Okay, at this point, I'm going to scale the second row by 1 divided by this number to get a 1 in that position so I can get it into actual reduced echelon form, which looks like this. And from here, I would do negative B times the second row and add that to the first row to clear away that B. Here's what that will look like. And so, yeah, cleared away the B here by doing negative B times this row plus the first row. Of course, the 0 here, 0 times anything doesn't do anything. Negative B times this fraction gives you plus BC over AD minus BC. And over here you have a negative BA divided by AD minus BC. And then we're just going to divide this whole thing by A, or scale the first row, by a factor of 1 over A. So it gets a little messy. You got a lot of these fractions involved after you divide both the 1 by A and these other things by A. But when you actually do the algebra and work this out, you'll find out that this actually just combines to become D divided by AD minus BC. And I'm skipping that step, but you can check it if you want. And so this actually gives you a formula for A inverse. It looks like A inverse is just going to be, we can actually notice that you have the factor of AD minus BC in all of these. Let's just factor that out so that you get D, A, negative C, and negative B left over. And this works as long as this all-important denominator thing is not 0. And you might also notice that I divided by some other things along the way, like I divided by A at one point. So actually the same row operations don't quite work if A is 0, but you can always just swap it until C is in the same place. And it should actually work, but I'm not actually going into all of those weeds. So this works. AD minus BC is not equal 0. And of course, that is the definition of the determinant of a 2 by 2 matrix. So here's that definition just written out because it's important enough to see it that way, that if you have any 2 by 2 matrix like this, this is the formula for what we call its determinant. And we'll talk about how to take determinants of larger square matrices later on. That's what chapter 3 is about. And determinants of square matrices in general have a lot of cool properties. And one of them is this fact that the determinant is equal to 0 if and only if the matrix is not invertible. And you can sort of see that this formula doesn't work. It would give you divided by 0 for the inverse if it was. So that's sort of one way to see why that fact is true. So here is our last example. Let's say we have a system of equations here, and we want to find the solution for x1 and x2 that makes this work. using inverses. So what do inverses have to do with this? Well, if we think of this as an ax equals b sort of equation, with the a, which is 8, -7, 5, -5, and we use -9, 11 for the b, then so finding x1 and x2 means we're finding the vector x that makes this work. And the trick is that what inverses have to do with this is that if you multiply both sides of this by a inverse, then on the left side, the a inverse times a cancels out, and you just get the identity matrix times x equals a inverse b. And the identity matrix times x is always just equal to x. So this actually gives you sort of a formula for finding x just based on the inverse and multiplying that by b. This is kind of like if I said to solve the equation 3 times y equals 7, and I said y was just a number, then what you would do is multiply both sides by 1/3. With regular numbers, it doesn't matter what order you do it in, and you just get y equals 7/3. Same idea here, it's just a matrix reciprocal sort of thing instead of just a 1 divided by the number. So we got to see if that a inverse exists. To do that, let's use this formula from up here. This should work for any old matrix that started with a, b, c, d. This is saying if we take the a and move that down here, and the d get swapped too, and also the c and the b just become negative instead of having their position swapped. So that's what this has to do, and then also multiply by the determinant on the outside. So let's try that here. We're going to first do 1 divided by the determinant. That's going to be 8 times -5, multiplying this way first, which will be -40. And then minus -7 times -5. That will become minus -35. And so that will work out to be -1 over -5 there. But then we're also going to take the 8 and -5 and swap their places, the ones in the A and the D positions, and then the -7 and the +5 change their signs to +7 and -5. And once you simplify this a bit, we're going to see we get 1 over -5 for that thing on the outside. We're going to multiply that by all the entries here to get A inverse is 1, -7, -7 over 5, and -8 over 5 here. So that's that. So now to get x, we're just going to do A inverse times B. So that means doing that 1 -7/5 times 1 -8/5 times -9/11. I'll pause it to work this out so you don't have to sit through it. You should get 2 -5. And you can check that with x1 and x2 really quick. You'll get 16 minus 25 is -9. That works. And -7 times 2 is -14. Plus 25 is 11. That sounds right. Here is a couple exercises for you to do to help these ideas sink in. So for number 1, I'm giving you A and telling you that A inverse is this matrix. Your job is to multiply them both ways. Do A times A inverse and also do A inverse times A. And make sure that both of them give you the identity matrix. And for number 2, it's got 3 parts. For each one of these matrices, try to find the inverse if possible, or if it's not possible, just say it's not an invertible matrix, and that's the answer. All right, see you in class. Bye.